Oh, thank you. Thank you for the nice introduction. I would just start by pointing out that this work has been a collaboration between the Carson Institute of Technology and the University of Melbourne. As you see, there are quite a number of authors that now are working for different institutions. So the idea of the work that I'm going to present to you is to investigate a method that deals with storage system under uncertain conditions. So let's start. What are the motivation behind this work? As you may know, it might be of interest to convert electrical energy into other energy carriers that have some storage capability. And this might be particularly interesting in the case where we have uncontrolled generation in remote location, which might be more dangerous to inject directly onto the grid, or wherever this other energy carrier, for example, hydrogen, is needed by itself for industrial application. And however, there might be some challenges involved with this energy conversion. And one of them is definitely the uncertainty that might affect some of the characteristics of the system. And for example, we might have to deal with uncertain energy prices or uncertain energy flows. And we have seen both of these aspects in previous presentations. So let me explain everything with a practical example, a quite simple one. Let us consider a virtual power plant that is coupling some uncontrolled generation, for example, from solar generation, with the possibility of converting electricity into hydrogen and back hydrogen into electricity. As we discussed before, some of the parameters of the characteristics of the system might be uncertain. For example, the uncertainty affects the solar generation, or we might have an uncertain hydrogen demand. As well, the real-time prices might not be known at the operation time. So what does managing such a system means? Basically, we have to answer a fundamental question, that is, when do we convert electrical energy into hydrogen, and when do we convert hydrogen back into electrical energy? And this question, we can help solving this question by means of model predictive control, which basically means to set up an optimization problem over a certain horizon. Here I use this bold notation to indicate vectors of a quantity over the optimization horizon, where we want to maximize the profit of this system such that the system constraints are satisfied. And here I consider very simple constraints. We have a storage dynamic, the storage state is bounded, and we also have bounded conversion among these energy carriers. I would like to point out here that we force the electrolyzer to convert half of the production from the solar generator into hydrogen. And this may be a needed constraint in all the locations where we cannot inject directly all the production of this certain solar generator into the grid without harming it. So this is basically a trivial problem to solve because it's linear, and it can be seen as a problem where we have an uncertain price in the cost function, and we have a state that is affected by an uncontrolled input and some controllable inputs. And both the state and the inputs are bounded. So what is the challenge in solving this problem? The challenge comes from uncertainty that might affect both the uncontrolled input and the uncertain price. And the traditional way to deal with this uncertainty is to make use of sampling-based methods, where basically the uncertain parameters are replaced by a set of their realization. And while these methods have proved efficient in many works, they still have some drawbacks. For example, the computational burden might be high because of the numerous problems that we have to solve, and it might be difficult to compute a meaningful set of samples that describes this uncertainty. Moreover, as we are trying to find a solution that is good under many circumstances, the solution is generally suboptimal for the actual realization. So the question that we try to answer is, are there alternative methods to deal with this problem? And before going into the details, I would like to give a general idea of what we try to do. So we can summarize everything with these 3 steps, which are, at first, we divide the first stage from the second stage decision variables. So if we have decision variables over the optimization horizon, we consider the first stage to be the one that are actually applied. So the first one in the horizon, while the remaining ones are the second stage decision variables that are not actually applied because the problem is solved again before the time in which they are considered. So the second step is that we go from an optimization problem, as the one we've seen before, to a mapping. Basically, we try to map the profile of the uncertain parameters and the current state to the optimal solution of the first stage. So the optimal first stage solution that is the one that we are actually applying. However, this mapping is still deterministic because it's basically going from a realization of the uncertain parameters to an optimal decision. So we have to introduce stochasticity, and we transform this problem such that we can now go from a probabilistic forecast of these parameters to a decision that has the highest probability of being optimal. So this is the general idea behind the scheme that I will now present in more details. However, before that, I would like to point out that we are restricting ourselves to certain kind of systems that are satisfying these two assumptions that you see on the top. Here, I reported the assumptions as they are written in the paper quite rigorously. However, we can summarize them with these 2 sentences. So we are considering systems where it's never profitable to purchase at a lower price just to sell later at a higher price. And this is because of the efficiency conversion, the efficiency of the conversion, as much as because of the price difference. That means that the main decision driver on whether to transform energy into hydrogen and vice versa is the price difference between the current price and the future price. This allows us to basically divide the decision variables in 2 kinds. The one that are occurring where the price is lower and the one at time steps where the price is higher. And further details are on the paper, but this is the general idea behind this assumption. The other assumption that we consider is the storage is quite large in the sense that it's not the storage constraint that is limiting the decision at the current step for most of the time. This reduces the space of solutions to 4 possible actions that are combinations of using the both conversion tools to their limits. Clearly, given the conversion efficiency, converting electricity into hydrogen and vice versa as much as we can at the same time is never a solution. That means that basically we have to deal with 3 possible solutions, that is converting as much electricity into hydrogen as we can, doing the reverse process, or doing nothing. And you may wonder whether these assumptions hold in reality. And to understand that, we decided to test this assumption on a real test case. And we consider a virtual power plant that is going to be installed in Port Lincoln in Australia that has the characteristics of the virtual power plant I showed you before. So we have a solar farm, we have an electrolyzer that allows us to produce hydrogen, and then we have an open cycle gas turbine that is converting hydrogen back into the electricity. We have quite a large hydrogen tank, and we are bidding on the wholesale energy market for Australia. So we are considering these prices in the energy exchanges with the grid. However, we consider that the hydrogen demand is known and fixed every day, is the same. So how do we test our assumptions? We compared a problem that is approximated compared to the one that I showed you before, and these approximations is due to the application of the assumptions that I presented, and you can find the details in the paper, with what we call the full information optimal control. that is basically solving the complete problem that I presented before, knowing the future realization of the uncertain parameter. So we consider as if there is no uncertainty. And regarding the assumption true, the fact that we are basically using just 3 possible actions for most of the time, we see the solution of this full information optimal control is basically one of the 3 cases that I presented before for most of the time. Just for a little more than 5% of the time, we have a solution that is not one of these. That means that the storage is actually limiting the action in that time step. Regarding assumption 1, instead, the comparison between the revenue obtained with the approximated problem with full knowledge and the complete problem with full knowledge shows that there is a difference of 7% in revenues. And this is quite high. So to reduce this gap, we applied an heuristic to the output of our algorithm, forcing the system to purchase energy whenever the price is very low. So what do we do basically? We have written the conditions under which each action is optimal. So in a nutshell, it is optimal to convert as much hydrogen into electricity whenever it is feasible to export, I mean, convert into electricity as much as we can whenever the price is higher than now. And this can be described mathematically by this equation. And at the same time, it's also convenient to export whenever, if we sell only when the price is higher than now, we will end up violating the upper bound of our storage limit, sometimes along the optimization horizon. On the reverse side, it is convenient to import whenever importing only when the price is lower than now will lead us to violate the lower bound of the storage constraint. And this is described by this equation. So now we have basically matched conditions on the parameters with an action to be taken. And the next step is that we move from these profiles that we've seen before, that are profiles in power, to an energy profile. And we basically have now that the conditions that I presented before are trivial inequalities on these energy parameters. And we basically have that whenever these energy parameters satisfied one of these equality, we can match this consequence to appropriate action to be taken. The last step is that these energy parameters are uncertain, while here we have deterministic equation. So the idea is that we compute quantiles, we compute probabilistic forecasts for these energy quantities that basically is computing the quantile for these certain quantities, and then we check whether these quantiles satisfy the equations that I presented before. And depending on whether the first two are satisfied, then we force the system to convert as much hydrogen into energy as it can. Instead, if the last condition is satisfied, that we force converting electricity into hydrogen as much as it is allowed. And if none of the conditions is satisfied, that we do nothing. And we tested this simple control algorithm into the test case that I presented before. And we have observed that there are two advantages of this method. What we compared our method with, we compared it with this full information optimal control problem that I discussed before, considering that this is the best that we can achieve. Of course, we see that we are much faster than the solving an optimization problem, because basically we are just checking whether some conditions are satisfied. We are not solving an optimization. So we can say that the computational burden is reduced compared to using whatever scenario forecast that would have certainly higher computational burden than the full information optimal control, which consider a perfect scenario forecast. And on the other side, we have observed that the revenues achieved by our control method are almost 90% of the full information optimal control algorithm. That is basically the maximum that we can achieve. So to summarize, what I presented is a method that allows us to operate a virtual power plant where we have large storage and we have to deal with uncertainty. The method is based on combining some probabilistic forecasts of some properly crafted energy parameters with a system of inequalities. And the results on this test case have shown that the revenues that our algorithm can achieve are quite good compared to the maximum we could potentially achieve knowing everything, and that the method is computationally cheap. Of course, we would like to extend the algorithm eventually to consider multiple storage system and different kind of applications, so restricting the, removing the restriction that the assumption we consider poses. And that's all. Thank you for the attention, and I would be happy to take any question you might have.
Great, thank you. Are there any questions? There's nothing in the chat box yet. Maybe one's coming in. Right, now there's one from Matt Deacon. Can you see it, or would you like me to read it?
Okay, yes. So the question is basically that on a real level, so do you think that a real virtual power plant operator might use such a simplified approach, given that you end up with less expected revenue? Well, we ended up with less revenue that the case in which we would know everything. So if you had perfect forecast, then yes, of course, this method would not give you better revenues, so you might not use it. However, this is not the case in reality. So to understand how much revenue loss or increase you would have, you would need to compare this method with another method that is considering stochastic predictions of the uncertain parameters. So we haven't done that because it's hard to decouple the result of such a method from the quality of the forecast. So, and we wanted to focus more on the method than on the forecast. I don't know if this answered the question. So if you have very good forecast, then maybe not, but in reality, you might have better results with such a scheme.
Mm-hmm. Okay, thanks. And I have a question. So what's the challenge associated with incorporating multiple storage systems? Is it mainly computational?
No, it's also the model that we use. So it's not mainly computational, because in the end, we consider this unique parameter, these energy parameters that are basically true, that we are then using to decide which action to take by checking these inequalities. So if you have multiple storage, then you might have to aggregate them in order to replicate this behavior. So if you can aggregate the storage, then this is doable. If you basically can represent all their states with one state. whether this is always possible or not, then this has to be seen on the system itself.
It's a modeling issue. Okay.
So yeah, it's basically a modeling issue.
Okay, great. Thank you.